Welcome to the ACF 50 Application Training Course. This program will help you to understand why corrosion starts, how to stop it and prevent it by using ACF 50, and recommended application techniques. We will also discuss why it makes sense for owner-operators and fleet managers to develop and maintain proactive corrosion prevention programs by using ACF 50. But first, let's take a look at what all metal airframes have in common when it comes to corrosion. With proper care, it's not unusual for metal airframes to last for decades. When they finally do succumb to deterioration, it happens in one of two ways. The first, mechanical damage, is fairly obvious and has a myriad of causes, which include abrasion, wear, fatigue, or actual collision. The other, less obvious threat to airframe integrity is corrosion. Like a cancer, corrosion can eventually turn an airworthy airframe to junk when left undetected and untreated. This is especially true for older aircraft. For corrosion to start, several conditions must exist. First, two electrically conductive dissimilar surfaces must be in physical contact with each other. One surface serves as an anode and the other a cathode. When contaminated by a conductive liquid, which becomes an electrolyte, minute electrical currents start to flow. The corrosion process is like a battery, and it's this current flow, or electrolysis, that starts corrosion. Sources for these conductive liquids, or electrolytes, can originate as rain, humidity-induced condensation, soft drinks or juices, de-icing or toilet fluids, or even exhaust gas deposits that have been exposed to moisture. The corrosion arising from this contamination results in the metal slowly being converted or eaten away by the electrical current through the electrolyte. As long as the electrolyte is present, corrosion will continue to replace the metal with a powdery waste product. Left untreated, corrosion will ultimately threaten the structural integrity of the airframe, and the results can range from expensive to catastrophic. In fact, the typical cost of repairing corrosion-related damage compared to the cost of preventing it is about 100 to 1. For this reason, aircraft manufacturers use a variety of methods to inhibit corrosion and protect the airframe after it leaves the factory and is put into service. Typical anti-corrosion strategies include the careful placement of drain holes, use of corrosion-resistant metals, polymer sealants on fairing surfaces, primers and paints, and the use of wax coatings. None of these methods can guarantee a corrosion-free aircraft forever, and many start to quickly break down with age and number of cycles flown. Using sealant-type inhibitors can actually trap moisture next to a metal surface in some cases, or attract dust and dirt that speeds up the corrosion process. An effective corrosion inhibitor needs to protect the metal surface under a variety of conditions. It needs to remain physically active, penetrating all moisture-laden structures, removing the electrolyte and deactivating corrosion. Next, it must contain active inhibitors that prevent new corrosion formation. The corrosion inhibitor needs to have good dielectric properties to prevent electrolysis and be applicable to all aircraft structures and electrical components. ACF 50's unique chemistry meets all of these specifications.